As our presence on the internet continues to grow, so does the need to protect our private data. For the ultimate in network security, we can look to quantum mechanics. In this study, researchers tested a new quantum encryption procedure called the Round-Robin Differential Phase Shift Protocol, or RRDPS protocol. While conventional quantum cryptography methods are based on a system that checks for eavesdroppers, the new security protocol is based on a system in which the amount of information leaked to eavesdroppers is restricted by a fundamental principle of quantum mechanics, so that it does not require users to constantly keep an eye out for eavesdroppers. The RRDPS protocol is a type of encryption procedure known as quantum key distribution. Using conventional quantum key distribution, two trusted users, Alice and Bob, can communicate by sharing a secret key encoded in pulses of light. For example, in a conventional scheme called the Differential Phase Shift Protocol, Alice encrypts a set of pulses by applying a random phase shift to each one. Bob then reads out the train of information and measures the phase difference between adjacent pulses. One of the main advantages of quantum key distribution over classical encryption methods is that it operates based on the Heisenberg uncertainty principle, which states that observing a quantum system necessarily alters it. This allows QKD to indicate whether an outside observer, Eve, is trying to intercept Alice and Bob's key. The drawback, however, is that these QKD systems must continuously monitor the level of signal disturbance caused by an eavesdropper, which can compromise communication if the disturbance is large enough. In this study, scientists developed interferometers that add a small but important twist to the conventional QKD protocol to overcome the limitations of having to monitor signal disturbance. After Alice sends her encrypted train of pulses, Bob splits the one train into several instead of immediately reading out the information. Each of the split trains goes to an interferometer that introduces a different delay, specifically a unique multiplier of the pulse-to-pulse interval. The next step requires Bob to measure the interference between the original encrypted train and one of the new delay trains selected at random. In fact, because the pulse train is very weak, only one interferometer, which is randomly chosen by an optical splitter, allows for the interference to be detected. Bob then reconstructs the key based on the detection patterns and reads his results, except for the key itself, back to Alice. Because the pulse train is very weak, Eve cannot simultaneously read all possible reconstructed keys. The choice of which reconstructed key is used by Alice and Bob depends on the random choice of the interferometer. This means that no matter how much Eve tries to listen in on Alice and Bob's conversation, there is a limited amount of information she can possibly extract. That amount is determined only by the length of each train of pulses and the rate at which Bob reconstructs the shared key. The extra bit of randomness introduced by Bob when he delays the original train guarantees that the outside observer, Eve, will have limited information to reconstruct the key. This new quantum encryption protocol, which does not need to monitor Eve's actions, provides the ultimate platform for secure communication. To further improve the RRDPS protocol, the researchers expect to capitalize on advancements in optical waveguide technology that would facilitate the inclusion of more interferometers in their scheme. This would increase the number of delays introduced by Bob and would therefore make the encryption process even more complex and robust against outside interference.